Hi everybody. In this video we're going to start chapter 4. Chapter 4 is a pretty long chapter. There's 5 sections. So you'll be nice and busy for the next couple weeks. Just like chapter 3, you want to take this stuff real slowly. Don't be in a big rush to get the problems done. The stuff you see in the PowerPoints is really the same kind of stuff I put on tests. If there's problems on the homework you can't do, that's okay. Not everybody can do every homework problem. But just be able to do the basic concepts in the stat key. In this first section, there's no stat key, so it goes pretty smoothly. But it is a lot of definitions. So let's get started. All right, I'll let you read that on your own. Oh, wrong way. There we go. So first slide is estimation and testing. We saw this picture on an earlier slide a couple times in this class. About how statistical inference works. And we already saw in chapter 3 how to estimate a population parameter by using a confidence interval. So what we're going to do in chapter 4 is we're going to test data. And specifically, we test hypotheses, and that's the main focus of this first section. So the main idea here is that estimation uses the sample to give a interval estimate for the parameter, the unknown parameter. Testing is different. Testing takes a hypothesized value of a parameter. Instead of an unknown value, it's assumed or presumed to be some particular value. And then we use sample data to determine whether that hypothesized value makes sense or not based on the sample data. So it's 2 very different ways to approach it. All right, let's see how this works. So you want to use the same general approach as chapter 3. For every time you're doing a fairly complex problem, anything that even is like sort of a word problem, make sure you can do all these things. Determine the sample and population, count the number of variables, identify categorical or quantitative, explanatory and response variables, which you need sometimes, right? And of course, make sure you know the names and proper symbols for all population parameters and sample statistics. This stuff is just going on constantly behind the scenes. So the example we're going to use to establish the main concept is this study called Caffeine in Finger Taps. And this was a real study. And it's not a real complicated study. Sometimes I like to use stuff that students could do. This is a study that a student could do. Because a lot of the studies we do are real complicated, it doesn't mean stats has to be complicated. So does caffeine increase a person's finger tapping speed? So that is a statistical question, right? And we know now how to approach that, right? Take a random sample or a volunteer sample, randomly divide into groups the sample, so create 2 samples out of 1, and then give different treatments to each group. So it turns out that 10 volunteers were randomly assigned 200 milligrams of caffeine. It was a pill, not coffee or anything like that. And 10 others were given an identical pill with no active ingredient. Each subject tapped a finger as fast as possible for 1 minute, 1 hour after consuming the assigned treatment. So there's the data, right? So people can tap their fingers pretty fast, and remarkably similar numbers across the board. So you might be surprised by that. Now, if you're a drummer or something, you can probably tap your fingers like 500 times per minute, but the average person can do it around 250 times a minute. So this is a single-blind experimental study with the treatments randomly assigned. So what we want to know is, could this study possibly show that caffeine causes an increase in a person's finger tap speed? Well, as you saw on exam 1, because exam 1 covered chapters 1 and 2, we really, really emphasized the idea of cause and effect. So what do we need in order to show that caffeine is causing the increased finger tap speed? That's the question we're trying to answer, right? Right here. Does caffeine increase? Right? So increase means it's causing it to happen. Well, this is a randomly assigned experimental study. It's a comparative, randomized comparative experiment, as opposed to a matched pair. So yes, if the evidence is strong, if the data are conclusive, it will show a cause and effect relationship. So let's see how this works. So here's our box plots. Here's our summary statistics. And the idea is, up to this point in the class, this is really all we've been able to work with is, does it look like the finger tapping from the caffeine group is higher, significantly higher, than the placebo? So some of you out there are thinking definitely yes. Some of you are thinking definitely no. And some of you aren't sure. So let's really think about this, because this is the main thing we work on for the whole rest of this class, is sort of the process by which this works. So some of you are looking at this median and this median, and you're saying, well, this median is a lot bigger than this median. Okay, that is a legitimate argument. Others of you are saying, well, this overlaps this a bunch, and that might be too much overlap. Maybe that's too much overlap for a conclusive result. Okay, that is also a good argument. And some of you are saying, well, that both of the first two arguments are valid, and it turns out they are. So what wins? Does the amount of variability win when we're comparing these two things, or does the sample median being a certain distance win, and that tells us caffeine is in fact causing the finger tap increase? Well, it turns out it's much more complicated than a confidence interval, let's say. So let's see how this works. So we're actually interested in the differences in the populations that are represented by these samples. So I'm going to stop there and go back one slide. So pause it if you want to read that again. I'm going back one slide. These come from samples. Each sample is size 10. And we want to know, is the sample convincing enough for us to conclude that caffeine is causing the increased finger tap speed? So think about that as we go through this. So what you want to do is you want to think about what might happen if caffeine has no effect on finger taps. In other words, let's go back at this, going back a slide again. Does this look like what you would expect to see if caffeine has no effect? Say it out loud. I can't hear you, but I want you to say it out loud. You have to think through this stuff, or you're going to be very, very lost. Right? You're learning 100 years of statistics in a few months. That's hard. All right. So you should have said no. If caffeine does not have an effect on finger tapping, then this is not the box plots we would expect to see. That's important. So it turns out that if this is not what you'd expect to see just by random variation, then that tells us that this is a significant result. Now we just need to figure out what's the mechanism that we can use to show this. And that's where it gets complicated. The logic is not complicated. It's how it works. So we know from chapter 3 that sample statistics vary. So we know that there will be some variation in the sample means. So the box plots, we don't expect them to look exactly the same, right? And even if caffeine doesn't affect the finger tapping rate, we don't expect X bar C and X bar P to be the same, right? We expect there to be a little bit of variation, but how much are we willing to accept is just part of natural variability from samples, and how much is giving us information that's telling us the caffeine is causing what we see. So this is the way it works. If we determine the difference in the means is significant, so you might be thinking this is a significant difference. What does that mean if it is significant? Well, if it's significant, we can attribute the difference to two causes. It has to be either random variation. So this could happen from random variation. Remember, this was 20 people randomly split into groups. It's possible that 5 of the fast finger tappers just got put in the caffeine group. That could happen. So number 1 is certainly possible. Number 2, the difference really is due to the effect of the caffeine. How do we know which option to choose for this data set? And this is the essential question we're trying to answer. So every data set is going to have slightly different box plots. In fact, we're only looking at one of the parameters here, right? This is, our variables here is one categorical, one quantitative. So there's actually 5 different combinations of graphs we could look at and things like that. I just think this is the easiest one to understand the experimental design. It's not a real complicated experiment. So it turns out that no matter what we see in the data, either number 1 is correct or number 2 is correct. We just need a guideline that tells us which one of these is more likely to be correct for any given data set. So it's either from random variation or there is a significant result. And specifically with respect to this example, if there's a significant result, then that tells us caffeine is causing the difference. So both graphs here, so what I did is I made another graph, and the question that we're going to answer then is a slightly different question than the one that we saw before. Until we learn what the guidelines are specifically for, choice 1 here or choice 2, because that's a little more complicated. Instead, what we're going to do is we're going to say, well, which one is telling us more strongly, which one is more convincing that caffeine increases the finger tap speed? So what I did is I just made two new data sets. And you just have to look at these and say, which one looks more like it's just random variation and there's no cause coming from the caffeine. So you would choose this box plot over here, right? I called it TAPS B. I put on the left side, I don't know why. So this one looks more like random variation, right? The medians aren't exactly the same. With box plots, we can't see the means. But if the box plots are symmetric, then the means and the medians are the same or very close. So these means and medians are both right about here. So the means don't look the same, but they look really close. These two graphs look about the same. That tells us that it does not appear that caffeine is significantly causing any sort of increased finger tap speed. Over here, compared to the width of the box plots, these medians and means then are very far apart. So this one we would say is more convincing. So we're going to learn later in the chapter what exactly the threshold is for how convincing it needs to be. For now, we're just going to compare sets of graphs to each other or sample statistics to each other and say that one is giving us stronger evidence compared to the other. So one thing that gives students trouble in chapter 4 is just it's similar to the way chapter 3 was, is you have to remember all of the stuff going on behind the scenes as we progress through. These are not standalone sections. They're like coats of paint, right? One coat of paint by itself doesn't do anything. You have to go over it again and again and again and again. And once you go over it several times, you get a nice color, to keep the analogy going. So if the sample means are very close together, then we don't have much reason to believe that caffeine is causing anything to happen, right? And that's what we saw here on the left. Those sample means are pretty close together compared to the width of the graph, the overall spread. If the sample means are very far apart, then we have strong evidence the difference is caused by the caffeine. And so here's the crux of the whole thing that we're going to have to leave off. This last bullet, we're going to have to revisit in a later section because we just don't have the mechanism to discuss it any further. Any decisions we make about the effect of the caffeine is based on the likelihood that the observed differences are the result of random chance. So why would that be true? So I'm going to go back to the previous slide one more time, and we'll see if we can tie this all together. And then just hold on to that thought till you watch the next video, because the rest of this section is concerned with more of the definitions and behind-the-scenes workings of this. as opposed to the mechanisms. All right. So let's say both of these samples were the result of random chance, right? And what we do is we say, well, we assume caffeine has no effect. And that might seem silly. You might say, well, can't we assume caffeine has some sort of effect? Well, no. We know caffeine has certain effects on some people, but you can't just assume any old effect that you want, right? You can't assume that taking caffeine makes you a better Jeopardy contestant, right? You can't just assume anything you want. So we always just assume that caffeine has no effect. And you say, well, which one of these is more likely to be the result of just random chance, no effect? Well, this one looks very likely to happen, right? It looks just basically totally random. It doesn't look like anything's going on here. This one looks less random, right? It looks more like caffeine is causing some difference to occur. And that's the key to the whole argument, is which one looks like it is less likely to be the result of random chance and more likely to be the result of some cause and effect relationship. All right, so that's the end of that part. That's only the first example. Now we're going to look at a lot of the definitions, and we're going to tie up some of the loose ends, and that's the whole rest of the section. All right, definitions. A statistical test is used to determine whether results from a sample are convincing enough to allow us to conclude something about the population. A hypothesis is a claim that a parameter takes a certain value or is in a certain range of values. So here's where we start getting very technical, right? Up to this point, this has been a very non-technical discussion using concepts that we addressed in the first two chapters of the class. Now we're going to start bringing in ideas from chapter 3. So first thing, statistical test. A statistical test is different than like a medical test or other tests that you would see, right? Like a lie detector test. Doesn't quite mean the same thing. It's a special term. In statistics, if you see the word test, it means statistical test. However, we should be clear and always put the word statistical in front of it, because if I say, you have a test coming up in a couple weeks, it doesn't mean statistical test, right? It means an exam. So in the context of the material of the class, a test means that we're trying to determine if our sample is convincing enough to let us conclude something. And that's what we saw in the caffeine discussion, right? Did that sample provide convincing evidence that caffeine increases finger tapping speed? Don't know. We don't know how to determine that yet. But we would use a statistical test. And then at the bottom, a hypothesis. This is generally the same concept you would see in like a biology class, except in statistics, a hypothesis must contain numerical values in the form of how we define the parameter. Even though the parameter is unknown, we have to set it equal to some number, and then we're actually testing the hypothesis that the parameter is that number or isn't that number. So that's a little bit different. We'll see how that works later in this section. So let's talk more about when statistical tests are required or not required. So here's two examples. And we want to know, does the following analysis involve a statistical test or not? All right, so the first one is giving a Coke/Pepsi taste test to random people in New York City to determine if there is evidence for the claim that Pepsi is preferred. All right, so let's just focus on this one. So we see the word test. Does that mean it's a statistical test right away? No, it doesn't. Only in the context of like the explanations does test mean statistical test. A taste test is still a taste test. Well, that's a hard word to say. So what we have to do is go back and look at the definition. is used to determine whether results from a sample are convincing enough to allow us to conclude something. Is this question asking if the evidence is strong enough that we can conclude something? Well, we see the word evidence, so that's a good sign that it's a statistical test. The other keyword we're looking for is this word claim that Pepsi is preferred. So this is talking about in the population, even though it doesn't say anything about the population. It's implied that this is saying the claim that Pepsi is preferred in the population. So what happens is there's a lot of reading between the lines that goes on with this stuff. Once we hit not chapter 3, once we hit like the second half of section 3.1, all the claims we're making are about populations, or all the parameters we're interested in are about populations. So this one does need a statistical test. Why does it need a statistical test? That's something you'd have to put on an exam. A claim about a population is being tested using data from a sample. So what I did is basically paraphrase the definition. It checks all the boxes, so it needs a statistical test. All right, what about B? Testing 100 people in a driving simulator to find the average reaction time to hit the brakes when an object is seen in the view ahead. Again, we have the word test here. Does that mean it's a statistical test? Not necessarily. Could be, but it has nothing to do with that word. There's 100 people in a driving simulator. Okay, we have a sample. But we need something about evidence or a claim or a conclusion. We need the idea that we're trying to answer a question about something that is claimed. And there's nothing like that going on in this problem. So this does not need a statistical test. We could answer this question just with a confidence interval, right? We're only asked to find the average reaction time. So you have to do a lot of really sort of not deep thinking, but just cautious thinking when you're going through this stuff. Don't be in a big hurry. Like if you have to take notes, like from this, just to keep in front of you to do the homework, I highly recommend you do that. The homework jumps around a lot. Adaptive practice is going to jump around a lot. Exams are going to jump around a lot. You have to be able to keep all of this stuff sort of in your head while you're working through this. Moving on. So in example 1, we were talking about caffeine and finger tapping, and we had something called a null hypothesis, and that was that the caffeine had no effect, and that the population mean finger taps for people using caffeine is equal to the population mean finger taps for people using placebo. And that was the idea, right? Remember, we said, let's assume for a moment that caffeine has no effect on finger tap rate. Well, that's what we call the null hypothesis. And we write it as mu c equals mu p. So we're just saying and you can see that the symbols have their meanings here, right? So mu c equals mu p. So everything after the word population is wrapped up in this tiny little symbols, these tiny little symbols, right? The population mean, mu, finger tapping is our variable, finger tap rate, so the speed is our variable, taps per minute. C for caffeine is equal to the population mean, finger tap rate is our variable for placebo. So what happens is these symbols, writing it in this funny way that you'll eventually get used to. I had to take statistics at some point too. I remember seeing this for the first time, and I didn't like it the first time I saw it. But you just get used to it. It's a lot easier to write this than write all this nonsense every single time. Nobody wants to do that. Next up, we have something called an alternative hypothesis. The alternative hypothesis that caffeine had a positive effect on the population mean finger taps compared to placebo. And we write this alternative hypothesis as mu c greater than mu p. So what does that mean? Well, that means the mean finger tap rate in the population for caffeine is greater than, right, because it's counting number of taps per minute, so that's a speed, taps per minute is a rate, is greater than the mean for placebo. So this is the null hypothesis. It's what we had to assume in order for the data to give us information. And then this is what we think the data might show, or what we're looking for the data to show. So here are the generic definitions for a hypothesis test and null and alternative hypotheses. In a hypothesis test, we examine whether the sample data provides strong enough evidence to refute the null hypothesis and support the alternative hypothesis. So that's the basic idea, right? And if you ever get mixed up with this, always go back and think about the caffeine and finger taps example. I really think it's the best example, and it helps illustrate all of the concepts the best. So more definitions and terminology. So here is our definition for null hypothesis. We write H0, that's not an O, it's a 0. And so it's called null because null is 0. The claim there is no effect or no difference in the population or populations. Because you could be studying one population and you just want to know if there's an effect. But if you're studying two, we would say no difference. If you're studying one, you would say no effect. The alternative hypothesis is HA, claim for which we seek significant evidence. So get on those flashcards, folks. We're going to say the word hypothesis 200 times throughout the rest of the semester. So you need to know this stuff. It comes up over and over and over again in here. Got to learn these two. Null, no difference. Alternative is what we're looking, it's what we're seeking the claim. It's the claim for which we're seeking evidence. Sorry. Moving on. So it turns out that we've only seen one form of our null hypothesis, right? We saw this one here, mu c equals mu p. That's the only one we saw. But we know that we have 5 parameters in the class, right? In chapter 3, we had all 5 of these. So this chart will help you navigate how to write the null hypothesis. The parameter is related to the null hypothesis, but it's not the same thing. So you can always generally form your null hypothesis by saying parameter equals a number. If you say that, so let's say let's go look at this one, because this is what we were talking about here with our finger taps, right? So the parameter is mu1 minus mu2, right? That's the parameter. However, we discussed our null hypothesis as being mu c minus mu p for the caffeine example. Well, we could write that as mu c minus mu p equals 0. You're allowed to write it either way. This is the form that's preferred on the homework. So on a test, I really don't mind which one you use. And in the real world, these are used fairly equally, but this is the one the homework prefers. So remember, if mu c equals mu p, then the difference is 0 because you can subtract mu p from both sides, and on the right side, mu p minus itself is 0. So the way this works, the general form of the null hypothesis is always the parameter equals a number. I cannot stress this enough. This is one of the most missed things in this class. When mu has this symbol next to it, it's a number, like 6.5 or whatever, just some number. When mu is written by itself, it is a symbol that stands for the population mean of whatever the population is. Same with p. When we write p equals p0, p0 or p null is a number. So here's just a made-up example, 0.08. So p is a number, but it's unknown. It is the parameter in the population. P0 is a number that is known in the sense that it is conjectured, or it is what we're testing with our hypothesis test or statistical test. So you can see the similarity here, right? If you know your parameters, you can just set these equal to 0, and that's the general form of your null hypothesis in all cases. The only difference are the single variable ones. So notice these 3 here have two variables. If it has one variable, quantitative or categorical, then you have to write the parameter equals some other number. It could be 0, but it could be a different number. But if there are multiple variables, one quantitative, one categorical, two categorical, or two quantitative, you just write your parameter, set it equal to 0, and then just for an example, I mean, these never change, but I put letters in here just to show you, like, when we say mu1 and mu2, that could be, you know, mu c and mu p. But here, these two values are numbers. And that's something that a lot of students miss, and a lot of students think that this is mu. It's not. Mu is still mu. This is just the numerical value present in our null hypothesis. So we call it mu0, p0, or just 0. So I'm not sure the best way to remember that other than make flashcards and underline stuff. Print this out and highlight and underline things. Because we're reaching the point now where we're picking up information so quickly. If you're not caught up to this point, like if you didn't do well in chapter 3, this stuff probably looks like Greek. Let's talk more about alternative hypotheses. So a hypothesis test determines whether the sample data provide enough evidence to support the alternative hypothesis. The alternative hypothesis presents a range of values that represent an effect of some type. These can include symbols greater than, less than, or not equal, depending on the question we're trying to answer. So what we saw with the caffeine and finger taps was that our alternative hypothesis had a greater than symbol because the researchers were interested in whether the data would show that caffeine increased the finger tap rate. Significantly, right? Not just increase a little bit, but like significantly. So when analyzing a new study, we can't presume there is an effect or a difference in the populations. We require that the data provide significant evidence to draw any conclusions. So just keep that in mind, right? That this is what we're thinking the data will show, but we need significant evidence. So the study will say, if it says increased, then your alternative hypothesis will have a greater than symbol. If it says decreased or lowers or less than, then use less than. And then it'll say equal to or not equal to, use not equals. Let's see how that works. So here are 3 examples, and we're going to state the population parameters of interest and the null and alternative hypotheses. We've already seen the first one, right? That was our Coke Pepsi taste test. So how do we approach a problem like this? We already know how to do population parameters of interest, right? Because we did it in chapter 3. So the only thing we need to be able to do, so let's go back and look at the chart a few slides back. All we need to be able to do is once we identify our parameter, choose the correct general form of the null hypothesis, and then select the proper symbol for the alternative hypothesis. All right, so what is the parameter for this problem? So if you're not sure, then pause the video and think about it. Because I think this is just, I'm going to rant for a second. A lot of students come into a class like this thinking that if they just see enough examples, they're going to get the hang of it. That's not how statistics works. Statistics has too many rules that are all in play at the same time, right? It's like trying to figure out, you know, pro football, NFL football by just watching it. It takes years to figure out how the sport works by just watching it. If you want to figure out how it works, read the rules, right? Well, this is similar. We have some rules for this. Use the guidelines that I gave you at the beginning of the slides here and break it down. So it's a Coke versus Pepsi taste test. So it's definitely a categorical response variable. Is there an explanatory variable? Think about it. Pause the video and say it out loud and then restart it. All right, so we have a categorical response variable. There is no explanatory variable. So that means the population parameter is P. And then we have to state what the parameter is. Like, what does it mean? Well, P is the proportion of New York City residents who prefer Pepsi, right? Over Coke, right? If you didn't get all of that from that little problem, go back and try it again and start taking notes inside the problem and piece this thing back together. You are not going to just brute force your way through this stuff, guys. Nobody can do that. You have to disassemble the problem, move it around, and then like put it in little boxes, and then go through the boxes and fill it back up. All right, so let's go back. So we know what P is. So I'm going back 2 slides to show you how this works. Our parameter is P. That means the general form of our null hypothesis is going to be P equals some number. What number do I put there? If you look at this problem, we're not given any numbers. So the way you remember it is say to yourself, the null hypothesis means no effect or no difference. If there's no difference between Coke and Pepsi preference, then what is the proportion who prefer Pepsi? Right? It's 0.5. And then the alternative hypothesis is easier to see now. All you have to do is change this equal sign to a greater than. And this is what we're looking for significant evidence to support. Is there evidence that the proportion of New York City residents who prefer Pepsi over Coke is greater than 1/2? And if the proportion is greater than 1/2, that means more people in New York City prefer Pepsi over Coke. So it can be claimed to have a majority, which is really what we're trying to show here in this problem. So it's a lot of breaking everything down, but you're not going to be able to do these problems unless you understand everything at every level. If you are lost or confused about anything at any level for relatively simple problems like this one, go back, look back through everything we've done so far in the class. I know that's a lot of work, but it's worth it because this stuff, believe it or not, does get more complicated. All right, part B. Determining whether a significant negative correlation exists between the weight of a vehicle and how many miles it can drive per gallon of gasoline in miles per gallon. Well, we see the word correlation. So that tells you that the population parameter is rho. So let's go back 2 slides. If the parameter is rho, then we're just going to write rho equals 0. That's just how it works. It's always rho equals 0. So that was easy for our null hypothesis. What is the alternative hypothesis? Well, we have a negative correlation. And remember, rho is the correlation, right? So if it's a negative correlation, so rho is the population correlation, that means the alternative hypothesis would be that rho is less than 0 because we're looking for evidence of a significant negative correlation. If the problem said positive correlation, put a greater than. If it's just said significant correlation, put a not equals, because it doesn't matter if it's positive or negative, if it says significant. All right, last one. Testing to see if there is evidence that the mean time studying per week is different between first year and second year college students. All right, well, we have the word mean, so that tells you that it's mu or mu1 minus mu2 is our parameter. We can see the word difference here, and then we have first year and second year college students. So we have 2 different populations, right? First year college students and second year college students are different populations. That tells us that we have a categorical explanatory variable here, which is year in college. That tells us the parameter is mu1 minus mu2. And we'll just use 1 and 2 because it's first year, second year. That's easy to remember. So our parameter then is the difference in the mean study time, right, per week. So what's our null hypothesis here? Well, the null is always mu1 minus mu2 equals 0. When you have more than one variable, it's always equals 0. What about the alternative? Well, we're not told anything in the problem about greater than or less than. We see the word different. Different means not equal. So that is our alternative hypothesis, not equal. I wish I had time to show you every combination of parameters and alternative hypotheses. It would take hours. So here we saw 3 different parameters, 3 different alternative hypotheses, right? We have a greater than, less than, not equal. You have 5 parameters and 3 ways to do the alternative hypothesis. So there's 30 combinations. I'm sorry, 15 combinations, but later on we're going to see that it's actually 30. Learn this stuff now, guys. Don't wait. You're not going to get a ton of practice. That's why I give you all those practice problems at the end of the slide so you can keep working. So hopefully you got a general idea what's going on here. And if you get confused, go back and do this one again. This is a good study tool, this example. Notation caution. So this is something students mess up all the time, and you can guarantee it'll be on the exam. Hypotheses are written in terms of the population parameters, such as mu c and mu p, not in terms of the sample statistics, x bar c and x bar p. In example 1, it is not correct to write that the null hypothesis is x bar c minus x bar p versus the alternative that x bar c is greater than x bar p, because we know the values of those statistics by directly analyzing the sample data. In other words, information from a sample is readily available to researchers and, by proxy, us, because we have access to that data. So what we do is we don't use sample statistics in the hypotheses. It's not correct, and it doesn't make any sense to do it. Second bullet, when we write the null hypothesis is mu c equals mu p versus the alternative, that mu c is greater than mu p, we are stating that we don't know the values of the parameters, and we're looking for evidence provided by the sample data that supports the alternative hypothesis. So it's more like just a real formal statement. Hypotheses written correctly are very formal. It's almost like the proceedings in a court of law, right? It has to go a certain way because we need to set everything up so that when we get an answer, we need to be able to interpret that answer. We haven't seen how to answer this question yet, because this is the problem we started in the very beginning of this slideshow with the caffeine and the finger taps. We don't know yet how to determine if that evidence is strong enough. So we have to start these problems with this statement of, here's what we know, here's what we don't know, here's the sample, and all that kind of stuff. And then when we get the answer, we can just plug in, yep, it's that, or yep, it's that. So it kind of gives us some choices that we can make. And we'll see how to do that in the next couple sections. So we saw in section 3.1 that sample statistics farther away from the parameter value are less likely to occur by random chance. If these unlikely events lie in the same direction as the alternative hypothesis, then they provide stronger evidence that the alternative is true. That's what we saw with the caffeine and finger taps, right? The caffeine finger tap rate in the sample was higher than the placebo finger tap rate in the sample. So that gave us some evidence, or it was stronger evidence when compared to that other graph. If unlikely events lie in the opposite direction as the alternative hypothesis, then they provide weaker evidence against the null, or possibly none at all. If our box plots would have shown us, so I'll try to do this with my hands. Everything's backwards though. So the box plots we saw, I don't have little box plots. The box plots we saw, the top graph was to the right. If the top graph had been to the left, then the evidence from the sample would point in the opposite direction as the alternative hypothesis. That would provide no evidence or very weak evidence. So let's see how this works. In 2018, Pew Research determined that 81% of U.S. adults owned a smartphone. There's a link here to the study if you want to read it. A market researcher believes that this is not the current population percentage in Lorain County and takes 3 random samples to test this claim. Which sample statistics below provide the strongest evidence against the null hypothesis, P equals 81%, and in favor of the alternative, P is not equal to 81%? So it doesn't matter, from my view, if you write 81% or 0.81. The homework will make you do everything as decimals. On a test, I seriously don't care, because they're exactly the same thing. So you look at this and you're like, in the first sample, 134 own a smartphone out of a sample of size 200. Is that telling us that this is more likely to be true than that? Notice that without comparing these numbers, we have no way of determining this. What about 154 own a smartphone out of 200? Or 174 out of 200? So how would we be able to tell which one of these provides the strongest evidence that this is true and that this is false? So the way you do this is you just do little p hats for each one. I'm just going to do them all in my calculator and show you. It's not worth getting out the program. So here, I went, hold on, I need a little bit more light. I had a bunch of light here a second ago, but there we go. So 134 out of 200 is 0.67. 154 out of 200 is 0.77. 174 out of 200 is 0.87. So which of these statistics, p hat equals 0.67, 0.77, or 0.87, those are all p hats, they're different p hats, but we can call them all p hat. Which one provides the strongest evidence that p is not equal to 81%? Well, you would pick the one farthest away from the null parameter, because this is a two-sided alternative hypothesis. It doesn't matter what the evidence shows. Evidence farther away from the center will provide stronger evidence against the null hypothesis. Now, if this were a greater than sign, we couldn't use A. It would instead be C. So the evidence must point in the same direction as the alternative. For a two-sided alternative, it's either direction. And it must provide the strongest evidence, meaning it must be as far away from the center as possible. The center of the distribution. So what we're doing here is we're really using the idea of a sampling distribution, right? That we could go in and take lots and lots of samples. And here are 3 of them. So here's a similar question. Which sample provides the strongest evidence that the population mean for mathematics placement exam scores is greater than 25? So here's a bunch of samples. These are all about size 40 each, and these are some exam scores. Maybe think of it like the ACT. Maybe these are, classes or cohorts that took the ACT. So which one of these do you think is providing the strongest evidence that the population mean placement score is greater than 25? Well, you'd look at the means, right? So the mean of this is around 27. The mean here is like 20, so that's pretty low. We don't want that one. The mean here is like 26, and the mean here is like 30. So sample A would provide the strongest evidence overall that the population exam scores, placement scores, are greater than 25 because it's to the right. Which is providing the weakest evidence? Well, this one is providing the weakest evidence because it's going the wrong way. The average here is below 25. If we're looking for evidence that exam scores are above 25, then a sample below 25 is not really providing strong evidence. So sample A is the strongest evidence that the alternative hypothesis is true, and B, sample C would provide the weakest evidence, or no evidence at all. There's really no way for us to distinguish weak and zero evidence, so we'll just say weakest, just to be safe, because we don't know if it's zero evidence. All right, well, that's how it all works. That's the end of the slideshow. In the next one, we're going to keep going with chapter 4. And if you want more practice with alternative hypotheses, try these practice problems in the book. Plus, as usual, there's lots of videos in the ebook and things like that. That'll do it for this video. If you have any questions, let me know, and I'll see you next time. Bye-bye now.